Hi everybody. So I want to do a second quiz on graph isomorphisms because it's an important problem and it also is a way to see a bit our paths that we're going to use, because this will be on using paths in order to determine whether two are isomorphic or not. And if they are isomorphic, that's perhaps the bad scenario, worst case scenario for you, because then you have to provide me with an isomorphism. And if they're not, you have to give a reason they're not. So I'm going to do one of each. Of course, in the quiz you won't know which one it is, but so that you see a little bit what comes into play here. Okay, so we know that one thing that we need to look at graph invariants are degrees, and in particular the number of vertices of a certain degree has to be the same left and right. So let's look at what we have here. This is a degree 1, this has degree 3, this has okay, I think sorry, I forgot to draw one line here. This has to be yes, it has to be this here. Oops, not this line. So okay, so sorry. So this is degree 4. Sorry about that. This has degree 3, degree 2, degree 2, degree 4, and degree 2. And what we have here, 2, 2, 4, 4, 1, 3, and 2. So let's see what we have. Both have exactly one degree 1 vertex. They have 3 degree 2 vertices, 1 degree 3 vertex, and 2 degree 4 vertices. So there are we cannot distinguish them from each other just based on the number of degrees. Now we could look at neighborhoods, and I'm not saying that you might find something, but the whole thing is about paths, so I'm just going to just give one example. If you take the neighborhood of degree 4 here, it has a 1, a 2, and a 3, and a 4 neighbor. So it has neighbors of each type, and this one does the same thing, and this one doesn't. So that already tells us, okay, that tells us that this neighbor, this degree 4 is different than this degree 4, and the same here, right? This has 2, 2, and 3 neighbor, a 2, 2, 3, and a 4 neighbor, and here we have also a 2, 2, 3, and a 4 neighbor. So the 2 degree 4 are distinct. So if we know that there is an isomorphism, it will send this degree 4 to this degree 4 and this degree 4 to this degree 4. Moreover, this degree 1 has to be sent to this degree 1, right? Okay. Yes. And also the degree 3 has to be sent to degree 3. So you might be very optimistic that we are dealing here with an isomorphic graphs, because the neighborhood, at least we looked at degree 4, degree 3, and degree 1, they seemed quite to be the same, right? Just to the degree 3 guy, there's only 1, 4, 4, and 2, degree 3, 4, 4, and 2. So everything seems to match, and but there is a difference. So let's leave the degrees. So I said it in words. I should have perhaps written it down. I'm sorry about that, but I hope you same degrees, right? Just let me summarize. And neighbors have same degrees. At least for the ones that I've checked. I didn't check all of them, and neighbors seem to have same degrees. So I would be inclined to think I have an isomorphism because a lot of things match. But let's look at paths. We should look at paths. Okay. Or rather circuits. So okay, I say paths, but no, let me say circuits really. It is really circuits that we should look at. Paths is also something that we can look at, but they're harder to tell apart, right? Because a path is an end and a beginning point, so there's more ways to match one path from the left to a path somewhere in the right. You can move around, because where a circuit is something that is like, yeah, it's a circuit. So let's look at circuit. And of course, I always mean circuit, simple circuit here. So circuits of degree 3. So let's degree 3, length 3. So how much do you have in G? So here is G and here is H, right? So in G we have one triangle, two triangles, and I think there's only two. I only see two triangles. As I said, triangles are always rather quick to observe, and here it's the same, two triangles. Okay, so two here, two there. So that doesn't distinguish them. Length 4. Remember, there's no length 2 circuits, so length 4. Well, I can go around this way. I can go around this way, and I think because this, any other, if using this one, it was either a triangle or a degree 5, so no, that doesn't work. What about degree 4? There is this degree 4, and then there is this degree 4. Okay. Okay, so there are two parts of length 4. And then there's the parts of length 5. There is this one here that we saw, and I don't think there's 1, 2, 3, 4, 5, 6, 7. No, these are longer parts. Remember, it says 1, 2, 3, 4, 5, 6 is not allowed because I'm using this edge, right? That would not be a simple circuit. So I keep saying part, but I meant the circuit here, right? So there seems to be one of 5, and there's also one here. I don't think there's another one here. This one, 1, 2, 3, 4, 5, 6, 7. So they are too long. So again, everything seems to hint at the fact that we are dealing here length 5. So 1. I didn't look at length 6 and 7 and 8 yet. So we might think, I think we are dealing here with isomorphic graphs. But I want to check the parts of length 4 a little bit better. So let's write the part of length 4 here. There are two of them, and let's look at the degrees. So walk in this part and you see the sequence. So here are the parts. So I'm going to look at these, and I'm not listing the degrees on these parts, on these circuits. So instead of listing the vertices, I'm just going to list the degree of that vertex. So this part is a 4, from 4 to 4, 3. So there's this 4, I start at 4, then I go 2, then I go to 4, and I go to 3. That's one of them. And the other one is, I can start at this 4, 4, 2, 2, 3. So 4, 2, 2, 3. Okay? But let's look at what, so this was for G. So what happens in H? So here, I'm sorry, a little bit, okay, here's my H. So let's look at the length 4 part in H. There are two of them again. So one is this one. So if I enumerate it, it would be 4, 4, 2, 2. And the other part is 4, 3, 2, 4. But look at what happens here. These parts are not the same as the degrees are concerned, because in both parts here, the two degree 4 are adjacent. Of course, this, remember, it's a part, right? So this degree 4 connects to this degree 4. So we have these are adjacent and these are adjacent. But this doesn't happen here. You cannot by a part of length. In fact, this part doesn't even have a degree 4. Where these both parts have degree 4. So another way of saying this, there's no way that I can match this part to any of because, sorry, I keep saying parts, I meant circuits. Because circuits of a certain length are graph invariants, they have to be sent to a circuit of the same length, simple circuits of the same length. This simple circuit has to be sent either to this or that, but it's impossible because these both contain degree 4 and this doesn't. And so that's how they tell apart. It's subtle, I agree, but this is a way of telling them apart. And I'm not sure that I didn't really look for the high 6, 7, 8. They are very much harder to find, parts of this big length, right? So there's a 1, 2, 3, 4, 5, 6. There's a 1, 2, 3, 4, 5, 6. But those parts, because they're becoming so long, they're already different. No, I shouldn't say that. But So we could ask the same thing of our triangles. I looked at the length 4 once, and I saw that the circuits are different. Let's look what is the length 3. The three triangles is a 4-4-2 triangle. So this is a let me write it. I should have perhaps put everything in red because I put degrees in red. So the length 3's is a 4-4-2. Sorry, 4-4-2. That would be this triangle, and the other one is a 4-4-3. Okay, so and a 4-4-3. What is the triangles here? One triangle is a here. One of the triangles is a 4-3-3. That's this triangle, right? 4-4. What I'm saying. Sorry about that. Or let's say let's go this way. 4-4-3. So it's a 4-4-3, and the other one is a 4-3-2. That's also different. Here we have both degree 4 lie on a triangle, whereas here there's only one triangle that contains both degree 4. So also at the level of triangles we see that something is not matching up. So let's perhaps indicate this in green here. This one cannot be matched with any of those two, where we had the same problem with this one here. Just by the virtue of the number of degree 4 vertices on it. Okay, okay. So that's yet a step further. Not just counting the number of paths, but also seeing how does this path look like through which points to which vertices of which degrees do they go. And then that's how you tell them apart. Okay, I said a lot in words, I didn't write it down, but I hope you understand where I'm going with this. Okay, here's another one. And so again, let's degrees, 2, this is degree 4, 2, 3, 3, 2, 1, 2, 3, 4, 2, 2, 3, and 3. And of course, I chose it so that, again, the number of degrees, so same number of degrees. Now we could look at the neighborhoods of these things. So let's look a little bit at, let's look at the degree 4 one, because that's, okay, if there's an isomorphism, it has to send this degree to 4 to this degree 4. And in particular, its neighborhood set should have the same degrees as this neighborhood set. So that's at least something that we should check. The degrees are 2, 2, 2, and 3. The degrees are 2, 2, 2, and 3. That matches. Okay. We could look at the degree 3 neighborhood of this, of degree 3 vertex. Its neighborhoods are 2, 3, and 2. 2, 3, and 2. That matches. And this also has, this one has a neighbor 3, 3, 2, and 4. Do we have this 2 here? Yeah, this one. This has 2, 3, and 4. So again, the same degrees and matching. Again, I didn't check every single one, seemingly matching degrees of neighborhoods, degrees of neighbors. In other words, the techniques that we had used in the previous quiz cannot distinguish these two graphs. Then we could look at paths. So let's look. Oh, there we go again. Circuits. Okay, circuits length 3. Length equals to 3. What do we have here? This is here we have I see one triangle and another triangle, so I have 2 of those. And here, oh sorry, let me do this in black. I don't know why I all of a sudden went in red, because I'm gonna use red for degrees. So okay, I want to write all this in black and then get a little bit cleaner anyway. This can go. I won't write these two other things. So we now looking at circuits. Here I'm gonna the length. So the length is 3. What we have, so this is my G and this is my H. Length equal to length. Yeah, let me give it. So here we have 2 triangles, right? And in here we also have 2 triangles. So 2 triangles. Now, since there are 2 of them, let's again list the degrees of these triangles. We have now seen in the previous example that's relevant information. So the 2 triangles, what are the degrees on it? The left triangle has degrees 2, 2, and 4. and the right triangle has degrees 3, 3, and 2. The order is not important, right? It's a triangle. And here, what are the degrees of the triangle? So I hope that you understand, these are degrees here. Not, I haven't named any of my nodes yet, vertices yet. I can't wait naming vertices until I really need to. So what are the triangles there? The inner, this triangle that I had was a 2, 2, 4. 2, 2, 4, oh, that matches that one. And the other one is a 3, 3, 2 or 2, 3, 3, whatever you wanted, but it's as a path, they are the same. So of course, yeah, be careful, right? It's not just, this is different. This is not just a set, this is an ordered set, right? It's the order in which we walk through these paths which distinguish this. This is another way of distinguishing this path from this path. Because this path has the 2 vertex is between the 2, 4. And here the 2 vertex is not immediately between the 2, 4, degree 4. So the order here is, it doesn't matter, it's a path or a circuit. Okay, so these don't match. Okay, so that doesn't tell me apart. Let's look perhaps at length 4. I see 1 square, and I think that's the only square. There's a 1 square, so, and that is actually, and in here we have also the outer square, there's 1 square. Okay, and so again, what are the degrees in this square? That is a 2, 3, 3, 4, 2, 3, 3, 4, and the degrees here is 2, 4, 3, 3. Now you say that's different. No, that's not different, because there is, okay, this is ordered, but it's a cyclic ordering, right? So this connects 2 to 4, so you have to read this as 2, 3, 3, 4, 2, 3, 3, 4, and then you can also do this way, 2, 3, 3, 4, 2, 3, 3, 4. You say, perhaps we could do here. No, this is different, right? This is, the in-betweenness is different. Here is a 2 in between, immediately 2 4s, and here this is not. Whichever you do it, it's not, because the 4s are next to each other. So there's nothing in between. Whereas here, we can go this way, and if we go the other way, so 2, 3, 3, 4, here is a 2, 3, 3, 4 path. Okay, so again, they're not distinguished. Degree 5, I think it is 1 degree 5, right? 1, 2, 3, 4, 5, and here there is 1, 2, 3, 4, 5, the same thing. This one would be 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4, 5, 6, 7, 8. You could try to find 1, 2, 3, 4, 5, 6, 7, 8, 9. No, got lost. Okay, you can different things here. Let me just mark down the 5 here. I'm not going to go to all of them. Length equals 5. So the path that I have of length 5 is, I'm going to again list its degree. 1, both have 1, so 1, and what are the degrees on this path? So I'll take a start here. Let's start with the 4, because that's unique, kind of, right? That's a unique guy. So 4, and then I go, let's say, clockwise, then go up 2, 3, 2, 3. And here I also start from the path 5 was this one, right? So I start 4, 3, 2, 3, 2. And again, 4, well, okay, it's not the same if I list it this way, 4, 3, 2, 3, 2, 4. It seems different, but this is because I run in the wrong direction. If I go this direction, it becomes the same. That is 4, 2, 3, 2, 3, right? Sorry, 4, 4, 2, 3, 2, 3, and then back to 4. So again, they are the same. So more and more, I'm kind of thinking this might be isomorphic. You might say, well, wouldn't that? You see, this is where these two are already getting different. They have the same number of paths, but different type of paths. Here we still don't have that. Okay, so if this is the case, I'm going to try to guess my isomorphism, and we do this. I'm going to do this again using colors. So first of all, I know that if degree 4 has to go to degree 4. But since I'm gonna design an isomorphism, at some point I'm gonna have to give names. So I'm gonna give names to this guy. So A, B, C, D, E, F, and G. And here let's say P, Q, R, S, T, U, and V. Okay, you need to know your alphabet here a little bit. Okay, so I know that D, the green D, has to go into the green V. That is already clear. What else can I be certain of? Well, I see there is, if I look at just triangles, I see there is one thing that the degree 4 is already taken care of. So let me perhaps match. This is already, we know where this goes. Then there are 2 degree 2s in the second one, and there's no 4 in the second. But this is a bit unique here. There's a unique degree 2 here and here. So for one thing, this part has to go to this part. Now that's not surprising because the degree 3s have to go to the degree 3s. So this degree 2 has to go to this degree 2. Let's localize them. So I'll put this in orange. So the orange, so the green is the unique. Let's give them names, okay? So the orange, what is the orange? Is the unique degree 2 on the 3, 3, 2 triangle. I mean, where the degrees are 3, 3, and 2. That's because each of them has exactly 1, and it has an exactly 1 degree 2 here. Okay, so that is 2, and so okay, just to be complete, this was the degree, is the degree 4 guy. Why am I overlapping so sloppy? Is the degree 4 vertex. Okay, so that also, we haven't located on in the graph itself yet. So where is this triangle? That is, we're talking about the right hand triangle, we're talking about this guy here, right? And in this case, we're talking about that guy. Okay, now, what else can we say? So the degree 3s, are they different? So we now looking, we know that the degree, so let's call them red now at the moment, but there are 2 red, so we're gonna have to do number red 1 and double red, right? We know that they have to be sent to each other. Is there a difference between them? Well, of course they both lie on this particular triangle here, but let's look at in respect to this distinguished one. So we cannot distinguish them as far from orange says, for me they're the same. I'm sorry, I don't see a difference. But green says, I see a big difference. One is my neighbor and the other one is not my neighbor. So this makes this guy special, and therefore, what is the degree 3 neighbor for this guy? That is this guy. So that means those 2 will map to each other, and the other 2, which I'm going to call the double ones, are mapped to also to each other. Okay? So I hope the color indications are clear. So we have 3 more degree 2s that we have to allocate. Now notice that what is left is there is 1 degree 2 that is still, of the 3 degree 2s, only one of them lies on a part of length 4. Right? This is the only one of the length 4. So okay, sorry, so this are the degree 3, and this is, so this is, what is the distinction between these 3? So these are degree 3, but the distinction is it's actually this one. This is the neighbor of degree 4. And the other one is not, but not therefore write it down. So that's how I distinguish them. Okay. So now I have to go for the degree 2s. I know that all the degrees 2s should map to each other, but there's one special one, that is this one. This is the only degree 2 that lies on a part of length 4. I could have immediately actually done this. I didn't need to know all the rest. There is indeed a unique degree 2 on this part. There's a 2, 3, 3, 4 part, and there's a unique degree 2 in there. So that's what these degrees almost always have these circuits. If you know that there are different types of circuits, you know that some things are unique there because there's only one of them. If there's only one of them, they must map to each other. Now, there are 2 3s, so we don't know that. There's 1 4, but we know already there's 1 4. Here, unfortunately, we cannot use that. Okay, so, but this is, again, tells us the 2 degree 2s apart. I identified it on the left, but on the right, it is this one. And then finally, we have these 2 guys. And as far as I can tell, I see no difference between them. Nobody can distinguish. The green guy says, okay, they're both my neighbors, and that's it. There's the only one that has to say anything about them. So there it seems that we have a little bit of freedom, and so I'm going to just randomly choose and say I goes to this guy and B goes to this guy. And now I have my isomorphism, and what remains is calculating the adjacency of both, and then compare. Okay, I'm going to do this by making myself, giving myself a bit space here. I hope all these arguments are now done. You can always rewind, right? This is the beauty of these videos, is you can stop them, you can go back, you can shout at me and I won't hear you. You can text while you do this, which is not smart. If you do this, if you want to text, do that and then return where you are. Don't let it run. Okay, so I'm going to put the alphabetic order. I don't know. I just feel this is what I can do. I'm not saying that is the smartest thing to do. I'm just lazy. I don't want to think too much anymore. Yes. Okay. Okay. So let's make this guy. So this is the adjacency matrix of G that I'm calculating here. So A is a neighbor of B and D. B is a neighbor of A and D. C is a neighbor of C. C is a neighbor of D, of E. That's it. And D is a neighbor of, sorry, my C's and D's are a little bit here. Sorry. D is a neighbor of what? E is a neighbor of A, of B, of C, and of F. E is a neighbor of C, F, and G. F is a neighbor of G and E. And G is a neighbor of E and F. E and F. Okay, and the rest is all zeros. You don't have to fill it in, but it's sometimes visually easier to see whether we have the same matrix. The second matrix that we're going to build has to be the same matrix. Now, how we build the second matrix, I hope you understand how this goes. The second matrix has to be these nodes listed in the same order under this correspondence. So my correspondence was colored, so let's do the coloring. So A, what was A? A was a purple guy, so A corresponds to a purple guy. So then we will have the B would be the double purple guy, so this would be the double purple guy. Then C was a blue guy. It's blue, I don't know which blue it was, this blue guy. Then D was a green guy. Okay, green guy. E was a double, well, E, yeah, I have to do it in the same order, right? It's the alphabetic order that I use, so I have to use that order. Double, and then F was a single, and then G was a orange. Okay, so let's now fill in what they are, the names of these. That is T, that is U, that is P, that is V, this is Q, this is S, and this is R. And so now, since we have to, I should have used line paper here. T, U, P, V, Q, S, R. I have to follow the same order, rows and columns. So one more time, I should have perhaps continued coloring this too, then you see it even visually. It visually becomes much clearer now if I do it this way, right? So, oh, that's not, I thought I'd changed the thing to green. Let me quickly do this. Green, and then the next one is double red, and that's a single red, and then finally orange. So the coloring is the correspondence. Okay, we normally have to write this down with A corresponds to T. So the way that you write it down is A maps to T or corresponds to T. You can do it either way. B corresponds to U, and etc. But I think it's visually much clearer, and you see what matters, and that's why you see this, is that the same color order we get here. Okay, this one I chose arbitrary. This one is determined, therefore, by the coloring, if you want. So if perhaps even you could think of it, you could just put a coloring as you want here, put the same coloring there, and then start filling in. Okay, let's now, a lot of talking, but let's check it here, because perhaps it's not right. So what are the neighbors of T? The neighbors of T are U and V. Okay. The neighbors of U are T and V. The neighbors of P, where is P? Yeah, P has two neighbors, V and Q. V and Q. V has a lot of neighbors, P, T, U, and S. Q has the neighbor P, S is a neighbor, and R is a neighbor. It's degree 3, so I have 3 ones, yeah. S, always checking that I don't forget anything by counting the number of ones, right? Because that's the degree. S, degree 3, so 3 ones. A Q neighbor, it has neighbor R, and the last neighbor is V, which is sitting there. Not alphabetic, it's sitting there. R, finally, but I think I'm done now, right? Oh no, wait, am I missing something? Q, what did I do? I did something. T is T, B and U, C and P, D and V, that is correct. E and Q, that is correct. F and S. Did I make a mistake with my F in this side, left side? Oh yeah, people. Why don't you tell me? I forgot, guy. F has also neighbor D. Yeah, of course, if I make a mistake, then it's not going to work. But why do I make a mistake? I know I made a mistake because this is degree 3 and I had only one. Luckily, because otherwise it would not match. Yeah, so be very careful when you do this. I know you all saw it and you were all screaming at me and I couldn't hear you, but okay, it's fixed now. And then finally R, where is my R, has two neighbors, Q and S. These guys. And it's, again, you see the pattern is now exactly the same. Let me just fill it in to completely see it. Now, you have to somehow, in your quiz, incorporate the same reasonings and visualize it. I'm not saying you need colors. If you have an app like Notability, you can use colors, but for many of you it might be hard. Some of you think that you need to type your answer, and I've told you this many times, I actually do not want you to type. I want you to write it. Okay? So please write your solution, draw it. You can make it somehow clear. You have a whole day time to make it a little bit nice and clean up a little bit if it gets a bit too messy. But give all the details that you need. Another thing I just wanted to say is, how should I have known that that I made a mistake, is because it was no symmetric. It was no longer, if this was a 0, this would have not been symmetric. Okay, here is the symmetry diagram. Okay, so that's how you should do it, and I hope you are able to do it.